Now, this picture that I have showed you earlier, you remember this picture. Now it might be more understandable to you. So this is a dimpled sphere, and the flow behind this sphere is being simulated with different numerical approaches. When you solve the Rance equations, in you see, you will get the average field. So you see very, very smooth field at the back of the sphere. And if you solve an average equations, you may get some vortex shedding, but you will not get any of the distorted vortex shapes, as you can see. So you will get very organized circular vortex shapes. And by increasing the complexity, meaning that from Rance to unsteady Rance, the details will be actually coming to your eyes. So you will see, for example, two vortices in here. Then if you increase it to a hybrid model that uses part of the Urans and uses parts of the simulation, you will see uh, not much, but the small number of vortices inside the wake, and then increasing to the large eddy simulation, and then the most complicated one, which is a DNS, will give you all these distorted vortex shapes. So the DNS is actually at the other extent, which is giving you the instantaneous field. There might be a question in your mind that, okay, how is it possible to have unsteady Rance, which kind of resolves time, because we are saying unsteady, which means that, okay, time is changing, but still we know that it came from averaged equations. We are talking about the U Rance right now. Okay, vortex shedding inherently is an unsteady problem. For example, in the case of the circular cylinder, there is a wake of circular cylinder, as you see in here, and there are alternating vortices, and you see alternating vortices, one in here, then one in here, then again one in here, and then one in here. These are alternating vortices from top and bottom of the cylinder. And if the Reynolds number is high enough and we are in a turbulent vortex shedding regime, then the alternating pattern is there, but the shape of the vortices will be irregular, and the shape will be different from each other. The thing is, when you solve unsteady Rance equations, it will be time dependent and it will give you vortex shedding, but it will give you the average value of the vortices. What does it mean, the average value of the vortices? In unsteady Rance, the data will be phase locked. Phase locked, you might remember it from the turbomachinery course as well. Phase locked relative to the body, there is a locked position at which the passing vortices will be averaged. And there is a perfect circular vortex at each point of the domain. So of course, the circular vortex will travel down with time, and we know at another delta t time, the vortex will be perfect circular, but travels down. So the unsteady Rance solution gives you the unsteady or time-dependent motion of the perfect circular vortices, not those very, very tiny. You see, these are many number of vortices in here. So it won't give you the uh, tiny irregular individual eddies or vortices. It will give you the, in fact, we are getting an ensemble averaging of those vortices, of these vortices. If you ensemble average, for example, these vortices in here, it will give you this shape that you see in here, right? Did you get my point?
So can we say that runs is normal average? U runs is ensemble average.
Yeah, exactly. RANS is time averaged, URANS is ensemble averaged. So you are able right now that you can see that if the process is steady, then you know that the time average and ensemble average are the same, right? That's why if you do the steady, let's say, process, if you solve the steady process with RANs and with URANs, you will get the same thing. The URANs only becomes for unsteady processes. So in a steady state solution, we neither see the individual vortices, you see it, no individual vortices, nor those circular vortices. So these are not okay appearing here again. So you don't see those. What you see is the wake pattern, only this pattern. This is the wake pattern. Okay, this is what the Rance equation gives you, the pattern. And while you plot the, let's say, for example, uh, mm, vorticity, you will see that uh, in here you have a different kind of color of vorticity, meaning that it is contra-rotating, and this is rotating vortices in this way. So this is, for example, in blue, and this one is red. So you're hoping that your turbulence model is fine. Depending on the accuracy of the model, the size of the wake is fine. So you say that, okay, the extent of the wake, this size of the wake, for example, you're hoping that these are fine. This will be accurate or not. So the CFD solvers give you actually the steady state solution, the RANS. Don't, as I said, don't get fooled by CFD, because this steady state thing does not exist in real life. In real life, you cannot generate something like this that you see here for in the RANs. In the laboratory, you don't see this thing. So I will show you some other results. Most of the time today we will go through the direct numerical simulation, but these are again some other results. For example, there is a backstep flow, and the flow is from the left to right, and there is a backward facing step. You see this step in here, and you can see the separation region in here. It starts separating, and the region that it is forming, the separation region, is this region. And as you can see, this is called the recirculation region, as you see. So there is a streamline which divides the separation region or recirculation region from the flow outside that is dividing the streamline. And at some extent, the flow will be again attached to the wall, and this extent will be called the reattachment zone. So what you see in here are the comparison between different approaches. So different approaches like DNS and like the PIV measurements, this is experimental, and then only RANS, K epsilon, and then LES. So you will see that there is a very huge difference between these approaches. And the exact thing that you have will be your DNS method, because DNS is directly solving everything. So if you solve the steady state solution, what you will get um, is the recirculation region. As you can see, for the K epsilon, you see this, and the streamlines will go like this. In all of these, you will see these streamlines, and inside of this, as we said, there is a vortex, and the reattachment distance is very important for us, as I said. So you see a lot of irregularities. There is no very a straight boundary. As you see, this is showing you some alias actually solution, but still you cannot see that boundary that that we are showing this boundary in here. You cannot actually detect that boundary. This is irregular flow. So the problem is when you directly solve for RANs, like using K epsilon in this part, and you hope that you can capture this reattachment distance, this distance that I showed you, the reattachment distance. When you do the DNS or LES, or when you do this experimentally, you will get the distance correctly. But in numerical solutions, you might not get that distance correct. Therefore, the fact that directly solving for the averaged values, which is faster and you can get the solutions much easier, but you have to implement the turbulence models that we are going to discuss to be able to solve these average equations because of their inaccuracies and their physical incapability of simulating real flow physics. Simply they cannot find the this reattachment distance accurately, and that's why people are trying to find better turbulence models, meaning that better turbulence model that can mimic the actual flow in a better way. So after all these examples, now we can start from the most straightforward turbulence simulation topic, which is direct numerical simulation. So direct numerical simulation does not involve any modeling at all. It solves directly the instantaneous equation. Before that, let's first jump to the previous session. You remember this chart when we talked about the energy spectrum and how the energy of turbulence um, is distributed among the wave numbers. Uh, we use the parameter wave number to indicate actual scales of eddies in the flow. And as you remember, these are all, these data that you see in here are all different data sets like wake boundary layer, pipe flow, round jet, even atmospheric boundary layer. And they were taken from 90, let's say 50s to 20,000s, in between 50, 40, 50 years, during these 40, 50 years. So what we get is, as you can see in the low wave number or large eddies, you see this part of the low wave numbers in here. In here, these are low wave numbers. Um, in this range, the flow is heavily dependent on the geometry. So you see that these are not the same. The energy levels are not the same. You see different energy levels, right? And it's very, as we said, it's very geometry dependent and boundary condition dependent. Because of that, the energy levels will be different. So the energy content, you can say the energy content in the oceanic boundary layer is completely different than the boundary layer in aircraft wing. But as you can see, after if you go towards higher wave numbers, so traveling towards higher wave numbers, meaning that you have smaller scales, all of these energies will collapse onto a one curve. So we have what we call inertial subrange. You remember the inertial subrange is this range, and then um, In the inertial subrange, you remember that the Kolmogorov predicted that the decay of energy with the wave number to the power of minus 5 over 3. So it happens to like this. So all of these show exactly the same behavior, regardless of the fact that where they came from. And if you go to higher, even higher wave numbers, for example, uh, from here to higher wave numbers, uh, uh, where the order of magnitude of Kolmogorov length scale will be larger, and the dissipation will be dominant. Again, you can see that all of these will collapse again together. So this is another line with a steeper, with a much more steeper than the minus 5 thirds. And this is given in the book as a kind of evidence of what we call universal behavior of turbulence. And if you're sufficiently far away from these wave numbers, sufficiently far away from the wave numbers that are geometry dependent, you will see a universal, a unique behavior of turbulence. And in the dissipation, you can see that as the wave number increases, then how fast the energy will drop. You see that the uh, actually the line is much steeper than the uh, slope of this curve, which is minus 5 to the third in the inertial subrange. And after all of these discussions, why do we still use instantaneous simulations? We said that these instantaneous simulations, they are very sensitive to initial conditions. They are very expensive, and in terms of engineering, they are not very applicable. The answer to this question is actually twofold. First of all, the simulations are not very applicable to engineering applications since the engineering needs solutions to be obtained very fast, almost every time. So it's not logical to wait some months to get some milliseconds of simulated data and then average it. Because um, at the end of the day, what you're getting from the simulation, you need to average it to be able to, for example, compare to some experiments. So you will wait 10 months, 10 years, even 10 years to solve for some milliseconds of data to simulate that milliseconds, and then you want to average it, so it's silly. But on the other hand, the simulated instantaneous data, for example, the results from DNS or LES, these are very valuable in terms of calibrating the turbulence models. How do we calibrate? For example, in turbulence models, we will see the turbulence models that we use to close the set of equations like k epsilon and k omega. They have many empirical constants, these k epsilon and k omega. And in their development process, they have many significant assumptions involved. So the problem is how can we check those empirical constants, whether they are correct or not? And for different kinds of flows, the coefficients will be correct or not. As an example, you can do a RANS analysis, and it can give you the Reynolds stress distribution, turbulent kinetic energy distribution. But if you collect the DNS data, since you have correct instantaneous fluctuations, and if you, let's say, have enough hard disk space, and you can collect enough number of instantaneous data, you can get real turbulent kinetic energy distribution. And then compare with the RANs, and if there is any fine tuning, that you can do on the RANS type turbulence models, then you can do and correct that. There are also other physical phenomena like stress and strain alignment. Um, so we know that turbulence stress has to be aligned with the flow strain. Why? We will see later. But we can check this from DNS data or experimental data like PIV data. But DNS data has a lot more resolution compared to PIV, spatial resolution and also time resolution. So let's continue with the introductory comments on DNS after we have a small break, actually. We will start talking about the direct numerical simulation. If there is any question, I'll be here to answer. If not, uh, I will ask for 5 minutes break.
You said that DNS has more resolution than PIV, right?
Yes,
Okay.
because again, once you are doing PIV, you are using a specific camera, and that camera, the camera gives you limited resolution, right? For example, you are using 4 megapixel or 8 megapixel camera for PIV.
Yes.
So your
Also,
resolution is restricted to 8 megapixel, limited to that one.
yes. Also, the particles, right? We are looking for the particles. They are
Yes,
not, they are
yes,
not
yes.
so much in air.
I mean, you have to seed the uh, flow, okay? So the particles inside the air, you have to seed the air. So you're seeding inside the air. You need to, for example, seed it with fog and or something else, helium swap bubbles. So the particles are not the air particles. First, they are not air particles, and second, they are much bigger than the real flow, real fluid. So that's why you're not getting that much resolution with your PIV.
Okay.
Okay, so we will continue after 5 minutes. Okay, so direct numerical simulation. By the way, do you understand what I'm talking about right now, or is it very hard for you to comprehend?
Actually, I can understand the main idea,
Mhm.
but you know that it's hard to understand the equations and
Do we have
math
any
mathematicals.
equations?
No, not now. I mean the
Okay.
behind the courses before.
Oh, okay. So, you don't see any equations so far, but you will see lots of equations. Okay?
Really?
So, yeah.
Okay.
Okay. So when you do DNS type of a study, basically you are resolving all the scales, meaning that from the largest scales, if you remember, we said integral length scales that are energetic and provide energy to turbulence, all the way to smaller scales, which we call them Kolmogorov scales, where we have dissipation. Dissipation, what does it mean? The energy dissipates into heat. So you will resolve all of them. You have to resolve everything. It doesn't involve any modeling, no modeling. The results that you get is a single realization of the flow. At some specific time, you just freeze the flow. At that instant of time, You will see all the details inside the flow. We know the equations. We have mass or continuity. We have momentum conservation. So it is conceptually, in fact, the simplest of all things. It cannot get any simpler than this because you have to solve Navier-Stokes equations. It's actually a brute force solution, meaning that you just have to discretize the equation, Navier-Stokes equation, and use the smallest possible grid size possible, I'm saying. And you have to choose the smallest time step and just resolve everything and start to integrate it numerically. This is this much simple.